Right, I'm Andy Page. I work at the Advanced Technology Centre, which is a BAE systems-wide research centre. It's partly based at Bristol, up at Filton. In the centre we have human factors experts looking at vision, right through to material scientists looking at silicon accelerometers, and then there's the computer people. Oh yes, so by GPU framework I mean not a library, but something where I can set up the state vectors I want and also supply the user kernels, so I can do anything on the state vectors I want. So why did I want to give a talk? I had a very illuminating 3 weeks working with ray tracing library Optics, which is an NVIDIA product. In that 3 weeks I was able to build a strawman, basically because it's got a good SDK with lots of examples. I was able to build on that. And what did that allow me to do? That allowed me to show to people in the operating divisions that I might be able to speed up certain parts of their design cycle. So NVIDIA, the optics library gives extreme performance, 100 million rays per second, well more than we need. And there are internal design processes which require ray tracing to do some modelling and help them choose a design. So I was intrigued by the need to just apply kernels. I thought it was very, very cool. These are simpler than CUDA kernels. You've got no concept of warps and threads, and a kernel can launch another ray. So that's how you get all these effects, which I'll show you a bit later on. Right. So I am sort of an old-style programmer. I probably like to do things myself. So for me to say using a framework is good means that it is pretty good. Optics has very good C++ support, which is almost crucial these days. None of us want to go back to C. And this all got me on to thinking about how we might use frameworks in other things that we do. Right, so I'm going to just show some examples from the SDK, and everyone cross their fingers because, see that, it does come up. All right, so what I'm showing here is shadow casting. So how that's achieved, I won't play again. How that's achieved is you fire a ray at the body of the cow. From that polygon you hit, you then fire a ray to all the light sources. And if you don't hit if you hit another polygon before you get to the light source, then that's shadowed. It's a shadow, and it's shadowed. All right. This one is collision detection. This just shows you that ray tracing doesn't need to be used to just generate an image. What this does is sends particles into a polygon scene, and each of those particles fires a ray out, and then it detects collision with geometry, basically. So there's no concept of an image plane. Every particle can fire any number of rays, so it's a totally flexible system. Again, glass refraction. I don't know exactly how that's working, but I suppose the rays are bending as you go from one interface to another interface. And then, so as well as me working on optics, I was aware of what some of my colleagues work, and one of them was working on a program, which is the wrong way around, should be Flame GPU. That's a particle agent interactor. So that's even simpler than supplying a kernel. You can supply it in text form, XML form, and then it parses the whole thing up into a simulation code. So it's a 2D code. Particles are in cells. I don't think they're in cells, but there's a distance filter. So and these particles send messages to other particles. I'm going to show just a second of this video because I'm going to show it a bit later, but up here you can see a few not pedestrians, but people exiting a building after a supposed some sort of chemical incident, and this was the sort of the end product of a project where we were the end users and Sheffield University were developing the Flame GPU code. Again, I was aware of a colleague asking NVIDIA about volume ray tracing, so that's different to the ray tracing I'm talking about, where you go from surface to surface. You go through a mesh. A mesh is a hexahedral mesh or tetrahedral mesh. So generating streamlines is quite a long process, and again, sort of plume propagation, you want to go through a bit like that diffraction program I showed earlier. You might go through a flume and refract as you go through different densities. And finally, we have an in-house SPH code, smooth particle hydrodynamics, probably a bit like the Laxman-Boltzmann code earlier. You measure, you sort of model the interface between between two radically different mediums by particles. So you have the ability for things to split off. This is supposedly an oil tanker going around a Formula One circuit. I don't know why. But you can see particles breaking off, sloshing around. So this might be used for, I think, the hydrodynamic ram type situations where you fire something into a fuel tank. The pressure's built up so huge it just explodes the tank. So that's the sort of thing you might be interested in. That. So that's as an in-house code. I think it might have come from America, from Australia originally. And I asked myself, would a sort of a combination of optics and Flame GPU give you a framework that we could use to accelerate that, and we just apply kernels and a state vector and do the physics on top of a highly tuned vendor-specific library. So going back to what I'm going to talk about then, so a GPU, as far as this talk is concerned, is I supply user-defined kernels, and I also define a state vector. And then it does all the tricky stuff in the background, supplying me, just calling my kernel when an interaction is happening. So in the talk, I'm going to talk about a sort of a modelling tool that was built on top of the straw man I talked about earlier, and this has been used it will be used in a few design cycles to look at infrared signatures, to look at just statistics for ray bounce interactions, and for sort of low frequency radar type applications. Also, I'm going to talk about us as an end user for Flame GPU, and also just speculate about what frameworks might be useful to us. So historically, our group at the ATC has supplied bespoke, cheap HPC solutions to the rest of the company. We've also supplied grid generation tools 15, 20 years ago. And so what are they? These are cell-based. Think of those, the Laxman-Boltzmann talk earlier. They're just rectangles in that you split space up into rectangles, and you follow particles or fluid flow through faces into other cells. So we looked at we do airflow over wings, water flow. Also, BAE is involved in building the Astute class submarines right through to Typhoon. So we've bitten the bullet moving from HPC to GPU, and we did that by pretty radical rewrite, throwing away our code and doing everything at a kernel-based level. To do that, you need to make all your loops independent loops. And this then goes back right to when I started. Basically, you have to color your loop so that at any point you do an update, the values you update are not going to be touched by other updates. So if you think of a 2D example, you have triangles, you have triangular elements with points, you're updating the points, and none of those points for elements in the same group are going to touch. And then we've used sort of some C++ template metaprogramming to allow us to sort of have proxy data, so that if we run it or compile it for a CPU, the data resides on the CPU, but if we do it for the GPU, the data actually resides and is converted from structure arrays to arrays of structures, all that sort of stuff, via the wrapping classes and template metaprogramming. We have our own GPU cluster up at Filton. That's 8 servers, 32 Fermi cards. However, we've done all this work, but we're also interested in whether, in time, I've called them mesh GPU frameworks might come on stream. So where I just supply cell and face kernels only, and I'm not quite sure whether it's O+2 or OP2 is a candidate. Pierre, who I worked with Mike as well. And there's also VTK, which is a mesh framework, and ParaView is built on top of VTK, and that allows some parallel processing. So you could sort of see in time that might move to enabling sort of transparent use of GPU hardware. Again, all possible because of the sort of high level of abstraction you get with C++. All right, so moving on to the tool I'm currently writing. So again, this was we had lucky enough to get 3 weeks' work to do a bit of investigation, prove to, or at least show to our customers that they could make a step change in their ray tracing tools. And it's based on NVIDIA's optics. So these divisions have already invested in ray tracing tools. They've converted them to HPC, but I was still able to show that I could get a 60x increase, like an hour to a minute, to do some processing. And going back to Intel's point, that probably means the original code is pretty badly, well, it's a hard problem. So I'm now going to go on to one of the things they're interested in is just pure bounce statistics. So this is on fixed and moving geometries. So we set up a system for them to do that. And I've lost my mouse. Yeah. So what this is doing, I'll leave you to guess why we might be interested in pipes. But this is a pipe where I'm tracing up to 32 bounces of array down the system, and this is live. Again, this used to take them. This was a batch process in the past. As it moves, it's only tracing a few of the arrays. Red area means that it bounces up to 32 times. So they're interested in looking at pipes. Another thing they're interested in looking at is infrared signatures, and that's, again, well, that's obvious why that is. And I'll show you an example of that a bit later. And again, lower frequency electromagnetic propagation, radar, Wi-Fi. And basically, we were able to convince our partners that optics could give a step change, and they've gone ahead and funded us on that. So I'm now going to talk about optics. It's geometry agnostic. All it knows is, well, all I have to give it is a routine which returns a bounding box for a primitive. So there's my primitive, a triangle. I return it a bounding box. So it then builds an acceleration structure, an octree or something. And when a ray passes through that bounding box, then it calls another kernel that I supply to do the fine detail intersection test. Groups of elements can be given different intersection and colouring physics kernels, so it's pretty general from that point of view. I mean, I've read somewhere that people think it's too general and that its performance is degraded because of that, but I don't think so. All state is stored in buffers that are mapped to the GPU, so there's no, from a programming point of view, I have, it's not quite as, it doesn't feel as complicated as doing a mem copy from the CPU to the GPU. So on the GPU side, I use an RT buffer, which is a sort of a template. That's a 2D float array, and on the CPU side, I use a string which accesses the context, and that returns me the same buffer. One thing that is very good is that you can see that this string has to match the name of the buffer. Sorry, I'm pointing at the screen here. The screen. So out has to match the string out. So this is a sort of thing I've played around in C#, and then you compile the code. It all looks so fine, but then when it runs, you get an error. You get a runtime error because you've misspelt the string. Optics has a very good validator just before you start tracing, which catches these sorts of errors. So that's very clever. And again, the geometry is part of my state. That is all. I can set that up in any way I want. Optics doesn't give me guidelines on how to do that or enforce me to do anything about that. So ray launch, again, I've mentioned all this earlier. It can be from an orthogonal or pinhole camera. In some cases, we're using ray tracing from surfaces, randomly from surfaces, and then the collision problem I showed earlier is basically the ray tracing comes from particles that are anywhere in the scene. So yes, it's a totally extendable or non-constrained way of launching rays. Again, a ray is tested against the bounding box. If it enters the bounding box, then my intersection kernel is triggered, user supplied, and then if I say it intersects, then optics launches my colouring kernel. User supplied, and the colouring can involve further rays, like the cow scattering problem, yeah, shadow casting problem. All right. So in conclusion, then, extremely fast, 100 million rays a second. There's no way you could code this yourself. Vendor optimized for their hardware. Very flexible, bug-free. I hardly ever have, well, don't have obscure bugs, really. Kernels are not complicated by the concept of warps. A simple sort of memory model, CPU to GPU mapping. The SDK contains lots of examples. All right, some issues. We'd rather have less rays per second and more ray depth. And the complexity of kernels is limited because we'd like to do intersection on bicubic patches, not just flat faceted patches. But we found that we couldn't really get the kernel complexity to do that. All right, some examples. Infrared signatures. To build a temperature map, we fire rays out from our image plane. They hit a patch. From that patch, we then fire a diffusive ray and a specular ray, We might fire the diffusive ray hundreds of times. They go out and sample other patches. We collect the temperatures back down to the original patch, and then that gets a float value at the image plane. There's a cut-off at which we stop tracing rays through the system, a temperature cut-off. The result of all this is that concave regions will get hotter and appear brighter in the screen. So I will show you this. So as I move the object, it then starts to trace diffusive rays randomly through the system and builds up this map. So every time I move it, it goes back to its default cold state. And then the thing to notice is that in concave regions, I'm getting slightly heating of the area. Basically, rays are bouncing around, hitting patches, and the temperature increases at the patch I view. Right. So, like I say, we've got a 60 times X speed up, and this starts to make you think about real-time analysis, or at least giving the designer the ability to play around with his design. Again, lower frequency interactions. The shooting bouncing ray approximate method is a way of getting an EM signature. We launch rays from a plane and observe them probably at the same plane. These rays bounce around the system, losing energy or getting absorbed by RAM in the system, and then end up back on the observation plane, and we do an integration on the central ray and a little ray tube around that ray. And again, we're in the process of updating existing tools using optics. All right, so changing tact. I'm now going to talk about an agent-based modelling system, Flame GPU. We were end users, Sheffield were the developers, and we've used this or tried to promoting it within the company, looking at evacuation on board a Type 26 frigate. They currently send off the design to consultant. They do the analysis and send it back 3 months later. So we're just trying to push the concept that this sort of thing could be done by the designer. So Flame GPU is an implementation of Flame. You can look that up on the internet for CUDA. I was talking to the guy yesterday. He's considered things like divergence. We talked about that earlier. You've got branching, you don't. So they pull agents that are in the same state and going to behave the same way. It's a cost-effective way of getting high-performance agent-based modelling simulation, a bit like Dave's system over there. And I'm not sure about this thing here. This could mean that it allows you to visualise or actually do runs on very large numbers, or it could also mean that they use the GPUs that are there to do the visualisation for you. Flame uses agents with state, X machines. You supply you describe your system partly in XML and partly in code, and then it uses standard XML parsing tools to convert that into simulation code. So I'm not going to go over this really. XML, some of it's in XML, some of it's in C code, gets parsed by an XSLT script, and you get your simulation program out at the other end. You define the messages you want these agents to understand, and you define the state and things like that. So agents are individuals with their own memory and perception. By perception we mean that they interact with neighbours, there's a neighbour. There'll be a neighbour filter, or so it's only going to interact with its a distance filter. So neighbours, use the distance to collect the neighbours, and then their behaviour is changed by their neighbours, and then if you're lucky, you might then end up with sort of gross system behaviours from all the agents interacting. So the sort of things you might model are pedestrian flow or flocking in animal behaviour. Like I said earlier, we were interested in showing to our operating companies, this is the Type 26, this is a floor plan for it, there are exits there, and we ran a number of simulations where exits were blocked. So this is still an ongoing discussion about whether they'll adopt this sort of tool. This is a sort of civil, chemical, biological incident. I'll run through the video in a second, but it involves people in the building coming out, initially just panicking and going off in any direction, and then some sort of control is imposed back onto the situation, and you try to pull people and then decontaminate them, and then they go out into a safe area on the outside. Right, so I'll run this. So pedestrians come out and they're allowed to move. So the incidents happened inside the building. Pedestrians come out of one or two, three exits. They're allowed to go in any old direction. I think the way the walls are modelled by agents, and the direction which the people go is also governed by agents on the floor, a sort of force field. And after a time, I say that some sort of control is imposed, and the pedestrians start moving towards holding areas. So I don't know where we are here. So notice the red people represent injured people. They're moving slightly slower. They're going to hold up the flow. So what we sort of imagine is that this sort of technology could be used not only for pre-planning, but actually during an incident. And also that leads on to, right, so pedestrians change their goal when a cordon is established. Those outside of a cordon are allowed to leak, so these people here escape without being decontaminated. Other people reverse their direction, start going back to the holding area. What we imagine this tool could be used in is like also in traffic modelling, so that you're feeding data in from a traffic system, and that affects and then you can start modelling from that position. So reasonably exciting things you can do with a tool like this. I can see Simon getting up, so I'll finish that. And I think very, very, very quickly then, going back to our sort of bread and butter element-based modelling, I talked about colouring. So we've been in the bullet, we've converted our HPC codes to GPUs. So I talked about colouring here, but there's another sort of interesting approach, and I call this one-sided or doing twice as much work. So what this means is, it's easy to think of this in an SPH type situation where I have two particles. The force on those two particles is symmetrical, yet to allow me to do a totally independent kernel update, I need each particle to just be in control of its own update. So that particle computes the force between those two particles, and it does the update, and the other particle does exactly the same. So I'm doing twice as much work, but it means I've got no locking in the code, no small colour groups. So basically, we program both these schemes inside our CFD solver. Again, we'd love to look at O+2 as an alternative. Keen to contrast solutions. And then on to my final conclusions. Optics performance made it easy for me to convince people to adopt it within the company. It's a vendor-tuned hardware system. You're not going to get that in a general framework. GPU Flame, versatile, cost-effective, allows real-time simulation, or they like to say faster than real-time simulation. And this could be used for planning and in the field live operation. That's quite. And then finally, I'd like to stimulate people from NVIDIA to think about SPH type frameworks. That's where you have particles moving 3D through a 3D cell system, and all we need to do is supply the kernels. And then finally, a watching brief on OP2. All right. Cheers, Anne.